So this talk I'm going to present, my name is Arash. I am a director of the HRI2 lab at the Italian Institute of Technology. I'm going to tell a little bit about physical AI for real-time adaptive interaction from autonomous control, human tracking to human-robot interaction. So let me just get into a few words, starting the motivation behind this work. Of course, we want to integrate AI into multiple, let's say, enablers such as human monitoring, human-robot interaction, and autonomous robots. But what we want our machines to do is to do more than just executing tasks, right? So they just need to understand, anticipate, adapt, and collaborate in physical work. I'm going to tell you just three principles about how this intelligence should be. And I'm going to build the rest of my presentation based on these three principles that I'm telling you in different contexts. So the first principle is that the intelligence must flow continuously, contextually, and consciously. Flow means that it should be transversal. Continuously means that it should be real time. It should be context aware, and consciously means that it should be goal driven. Just we all know about this. When we talk about physical AI, it needs to be growing with us. So it needs to adapt to our intent, our body language, and shared codes in real world when it comes to the human-robot interaction. And the third and most important, especially when it comes to robotics, is that the future of robotics lies in awareness across every point of interaction. So today's most of AI work is especially in robotics, is applied to spatial, let's say, scenarios when we are using robots to do trajectory planning or collision avoidance and other topics. But of course, this should be across all sections, for instance, including physical, when there are contacts between robots and humans and robots and uncertain environment, social aspects and cognitive aspects of the interaction as well. So I'm going to tell you how we are tackling this. This brings my talk to a physical AI continuum, I call it, that we work on different parts of this, from human monitoring to human-robot interaction and to autonomous intelligent robots. And I'll tell you how these three principles are being integrated and all that. Let's talk a little bit about the complex problem of human monitoring, right, through artificial intelligence. So there are many factors that we have to consider when we want to deal with humans, using systems to track humans and monitor humans and anticipate humans, and eventually use them to collaborate with robotics and automation or any other systems. So these components are, the first most is identity and the kinematics of the person. Then it comes to physical and cognitive, let's say, parameters of the person, and then eventually the interrelation between them. First, let's see about the kinematics. So this is a system that we have developed over the past years. Now it's ready, and we are actually in the commercialization and startup stage. So you can see you can set up whatever number of cameras that you want. With less than a minute calibration, you can have 3D tracking of multiple people in the scene. So here, basically, you will see 5 people being tracked only using 4 cameras, 4 RGB cameras, that we are processing them using our own, let's say, code. This is not using MediaPipe or open source or anything else. This is developed by us, that you can see not only the posture, but also the objects can be tracked in real time. If you're interested, please visit the website. We have, we can cover, this system can cover a large space, or you can use also these 2 cameras to give you the real-time kinematics of the person in real life. So what it can do with this is, the first thing is to render a personalized intelligence. So we trained a foundation model to be able to detect people using their features. So on the left and the right side, this is the same video. We are using our foundation model to detect the people on the left and right side anytime they are entering the scene. So at this point, you can see that their outfit is pretty identical, but we are able to detect the targets without any issues, and without really having some, let's say, mistakenly taking one for another. And this is only, if you're interested, please have a look at the paper below. So we are looking into main features, and by looking at the heat map and understanding through explainability, what are the most important key features in this heat map can actually be used to identify these people, and we are able to personalize in such, let's say, precise manner. Just let me give you some unpublished results that we have been doing. One of the main targets that we are looking into is to, for instance, to detect falls. We are looking into monitoring the consciousness of the drivers, like the car drivers. We had a talk just a few minutes ago, and some other applications that I will tell you a little bit about that. So this is a work that we have been recently working on, is basically using the skeletal features, purely kinematic, and LSTM-based anticipation of the human movement, plus a graph neural network. We are able to anticipate more than 500 milliseconds of a person falling. I don't know if you can see my laser pointer. Let me get this. So you can see here, up to here, given the posture of the person, the algorithm can anticipate what the eventual future posture of the person will look like. And this is the ground truth. So you can see that the emerging anticipation is very close and identical, basically, to person falling. This is under review for Roman. We just submitted there. And we have done this for tens of subjects falling with different trajectories, and our method can really nicely anticipate that. What we are looking into also to enable some, let's say, digital and smart gym activities. Here on the top left, you see a person just doing some simple gym activities. And here we are able to track not only the kinematics of the person, but also what object in terms of load the person is carrying, and it calculates all the physical dynamic loading of the skeleton that I will tell a little bit in a few slides from now. At the bottom, you can see how real time and how nicely you can track a person doing different, very dynamic movements, which is really hard using inertial-based systems and suits. Another work that we have been looking into is to be able to detect different, let's say, conditions of the drivers of the basically vehicles, not only to tell them if they are alert or not alert, but also trying to understand if there's a pathological issue behind that. So in this video, you can see. Let me go back. You can see using our algorithms that actually currently under review, but you can find it on arXiv. We are able to, using whole body key points and whole body language, we are able to distinguish between alert and not alert in different scenarios and pathological and issues that basically if somebody is having a stroke or someone is losing consciousness or something more serious that can be applied. So I'm also excited to tell you about something that probably you're the first ones seeing this. We are recently working on using basically detecting and classifying activity of people only using Wi-Fi. So if you think about it, especially for elderly case, if you want to track their movements and to anticipate if there's inactivity or falls, pretty much everyone has a home Wi-Fi of 2.5 or 2.4, 2.5 gigahertz at home. And basically what happens is that if a person does some movements within that range of Wi-Fi through the transmitter and receiver, the magnitude and phase of the signals change. So this is basically a person walking, and this skeleton is observed by the RGBD camera, right? So using some algorithms that we have just submitted to IEEE sensors, but you can also find it on arXiv, we are able to really nicely track the human skeleton. You can see on the right side, only relying on Wi-Fi. So using Wi-Fi signals, we are able to track the human's movements so nicely with the precision of less than a centimeter for each key points. Just to show you more, on the green background, you see the camera-based tracking. On the dark background, you can see the Wi-Fi-based tracking. The algorithm is quite detailed and elaborate. I'm not going to go through that, but we have different layers of convolutional neural network that it goes through a transformer and a decoder to be able to estimate the key points at the first step. So we can see how nicely we are able to only using Wi-Fi signals to track the skeleton of the person without using any visual information. What is really nice that after being able to track these key points, you can just pass it through DGNN, a graph neural networks, that you can actually classify the movements. For instance, here, only using Wi-Fi, it says walking, The class says squat here. And what is really nice that we can also anticipate the fall. Imagine you're some elderly at home. If they have inactivity or fall or different sorts of activities, by only using Wi-Fi, we can tell with a very good precision. So this was a little bit about identity and kinematics of the person. Now I want to tell you a bit about cognitive, let's say, monitoring. So in industry, usually the cognitive load is measured through questionnaires, which are highly inefficient and probably very biased. But in lab, we use EEGs and these fancy signals that are really cool, but probably they don't have industrial let's say, applicability. So in the deployability accuracy space, we wanted to be here, and we started looking into how we can have some intuitive interfaces, but at the same time accurate enough to be able to tell about cognitive load. So we looked into body language models like momentary diversion, nail biting, hyperactivity, and many other of those using only cameras and RGB or RGBD, let's say, based skeletal tracking by putting them together and through some calibration and identification. Please have a look at this paper. We are able to tell a lot about mental effort and stress levels of the person. So bringing this into human-robot interaction was for us very interesting because we could actually calibrate parameters of the robot based on the cognitive load. So the math here is a bit complicated, but just to give it in the simple words, if you consider a parallel-front optimization that basically some multidimensional parameters that here is 2, for example, are fighting against each other. So the robot can start with a slow, let's say, acceleration and jerk. Then it speeds up to bring to maximize jerk to improve productivity. But at the same time, when you detect stress, the stress means that maybe the trajectory of the robot, the jerk of the robot was too far beyond the limits, and then it comes back to this optimal point of that level of stress of that person in that day, basically calibrating the movements of the robot. Then we took it to a next level, said maybe we can actually look into how we can scale the safety areas of the person based on the attention and also stress levels of the people. Let me just quickly show you what happens. So at the moment in collaborative robotics, what we have is the safety areas, which are designed by the acceleration and inertia and some parameters of the robot, which are very, very conservative, and they are way beyond letting us to really have some collaborative, let go of physical collaborative tasks. So what we said maybe we can try to make it more intelligent, saying that we have some really strict boundaries, like this red one, that the robot should not ever penetrate this volume. But we have some scalable boundaries that, depending on the attention of the person towards the task and the cognitive load of the person, which changes the level of, let's say, the reaction time of the person to an unexpected behavior, then we can scale it up and down. So this path adaptation is based on timing law, let's say, optimality, and it comes down to this. So if a person is paying attention to the robot tracked by a camera, you can see here the attention cone, so to say, of the person is we are monitoring it. If the person is looking at the robot, robot is taking a less conservative trajectory and can get as close as possible to the robot. But if the person is not looking at the robot will take a more conservative approach. You can see here that it takes a longer distance with respect to the person because the person will have longer reaction time, right? Because the person is not paying attention. So we've then merged these two together. So basically the trajectory of the robot here, both is modulated through attention of the person and also cognitive level of the person. So this work is published in Transactions on Robotics just a month ago. If you're interested, please have a look. And there's a lot of interesting results that we're reporting there. The same line of thinking we extended to trust. Basically, in human-robot interaction, when you want to improve trust, usually they are all offline, and usually either based on questionnaires or really real-time and biological signals that mostly they are inefficient in terms of, let's say, real-time capacity or very complicated to be implemented. So again, we wanted it to be here in terms of deployability online trade-off, and we suggested for the first time a closed-loop optimization approach based on reinforcement learning. So how it works, just in simple words, you have a set of parameters that you think that they will contribute to better or worse trust of the person towards the robot, right? Then you can use a reinforcement learning algorithm like preference-based optimization, and the parameters of the controller of these three will change optimally based on the feedback the person will receive. So every time the algorithm will create a set of parameters based on whatever parameters you pick, and based on the feedback you receive, just simply asking the person if you like this new execution more than the previous one. So through few iterations, it converges to the most desirable and preferred parameters that you can see here. So here's the video. We only looked at this simple task of picking and pouring. We looked into the robot distance, robot velocity of getting close to the person, the distance the robot can basically move around the person, and the height of the object of the, cup to be poured. So here, Giulio was visiting my lab during his PhD that we did with this work. Eventually, what happens is that through 16 iterations, the person, along with other 20 subjects that we had, they communicate their basically preferences, and eventually all these, let's say, parameters of the controller converge to the desired preferences and eventually contribute to better and higher trust of the person towards the application of the robot in a closed loop manner and in an optimized manner. So the physical part of the model, I don't want to talk about it because maybe in previous presentations you have seen more of that. I have 7 minutes. I want to talk about some new stuff. So there are some references here. We have been working in my ERC project for 5 years on modeling of the human physical behavior during physical interaction, looking into compressive forces, using machine learning algorithms to find the contact points, relying on the torque equilibrium condition, looking into compressive forces when you're interacting with the physical world, not only the torques and stuff like that, and also maybe adding some complexity where the complexity of the physical, let's say the morphology of the body changes. For instance, the spinal cord, we modeled it like a flexible beam. But what I want to share is basically the most important thing in human-robot interaction is not to be able to decouple these values, but to find the intersection. So one of the first times that this intersection happened in a year or 2 years ago, we started looking into putting this in a reinforcement learning optimization algorithm that optimizes physical parameters, cognitive parameters, and robotic parameters. Let's call this productivity. You know, you want to be as fast as possible. You want to have less cycle times. You want to have better performances of the robot. So what happens that a reward was designed. This reward brought together cognitive ergonomic cost, physical ergonomic cost, and energy consumption cost of the robot to have the least energy consumption cost. Here you can actually have some time optimality for the task or anything you want. Putting the costs together, and after some iterations and through reinforcement learning, we were able to, after iterations, optimize for the robot's behavior to let's say optimize for cognitive, physical, and basically robot parts of the task. So we tested in several tasks, one of which was a handover, simple handover, for instance, looking into a robot holding a cup and passing it into the right angle with the right, let's say, approach angle of the cup, right? So this is the first iteration. Then putting all this together, looking into attention, cognitive and physical, let's say, costs and the robot consumption, it converged to the most optimum in terms of, let's say, theory. But what was really interesting for us, that when you optimize all these, let's say, parameters together, actually you're taking a very big step towards personalization. So we found out that after optimizing these three parameters, the eventual, let's say, handed over position and angle of the mug was the closest to what people actually wanted them to have without actually putting this parameter into optimization. So this parameter was never asked a person. So it was indirectly linked to the physical, cognitive, and cost of the robot. So basically, this brought some really side benefits that it helps indirectly go towards personalization to increase, let's say, effectiveness and acceptability of these systems. So we were quite happy about this, but we found out that there's this whole theory of coefficiency in motor behavior, that basically humans are coefficient. That's why we perceive everything natural. By coefficient, we mean that we meet in the middle of all the costs. So we don't optimize everything for our confronting partner. We optimize everything as a whole, and we arrive to a solution which is coefficient for both of us. So this solution was providing something similar. That's why the results were really cool. So I want to show just a few slides about very recent work we have been doing. We are trying to teach robots only by using offline videos. These results are published recently in two RAL and one transaction and robotics paper. They are available. Also, we have a data set called Handsome. You can download some of these works. So the theory here is that we are using information theory, which looks into basically the information flow between different players in a scene. So it's an offline video. You can have SAM segment anything or whatever visual perception that you have, but here for simplicity we use Oracle markers. So by applying information theory, we looked into mutual and transfer entropy between different, let's say, objects, which can be hands, left, right hand, and objects in the scene. We created the scene graph by segmenting it. We created this scene graph. The scene graph automatically created a behavior tree, and this behavior tree was automatically executable by the robot. So you show an offline video to the robot, and the robot creates this behavior. So there is absolutely zero coding involved. What is really nice is that it's not just learning black box trajectories, because when you have behavior trees, then explainability increases and the modularity increases as well. So you can replace blocks, add blocks. In the videos, we are showing that you can actually, if you lose some objects, or add some objects, or add new tasks, that this is scalable. We extended this in another paper to dual arm tasks, which was really nice. So the information theory, by looking at the mutual information and entropy of distance and other parameters of information theory, we could easily decode the segmented scenes, and these scenes were transmitted and created, and they could create behavior trees in real time, and the robots could execute that. The very last thing I want to show is just a very recent work that in the same framework we are bringing the interaction between humans and robots through large language models. So here what happens is that what I was explaining to you, we have scene representation. We are using information theory to get the entropy and, let's say, the uncertainty between whatever is interacting in the scene, right? With some good let's say, levels of uncertainty, we segment the scene. Then we create, let's say, a map through whatever you want to call it, through plan generation, but this is basically eventually goes through task segmentation, primitives extraction, role allocation, and then eventually it creates an adaptive behavior tree, but we close the loop with the human. So let me show you this video. I hope you can hear it. So this person is just showing, this is an offline video of a person pouring something, pretending to pour. And the robot, you can see it creates basically a context. And through the context using LLM, here we are using OpenAI's LLM, it creates, let's say, some context and adds some values. So it fails. The person starts interacting simply and intuitively to improve the. I don't know if you hear the voice of the video, but basically what happens, the person is looking into fixing some of the mistakes that the robot is doing. But long story short, we are telling that, okay, be careful, bring it higher and pour less. So these things through context awareness of the large language models immediately goes to numbers that changes these numbers automatically in the behavior trees. So initially the height of the key points were different. Now through the LLM and behavior tree, we are changing the heights. And initially the tilting was minus 90 degrees, and pouring less through LLM goes and automatically changes to this minus 60 degrees. Basically, it pours less. We showed this to different tasks like polishing and things like that, and cleaning. Here, for instance, Elena is showing something. When the robot is replicating, it's asking, okay, maybe clean the edges and stuff like that. And when the robot, for instance, is not attached because the force that this robot is replicating is wrong, through LLM, it basically this communicates with the robot and changes the amount of forces that the robot is applying, and also the actions. So I think I'm running out of time, but conclusions basically is to look into contextual intelligence and looking into basically the full messages that AI should basically really flow, and we need to really start looking into not only the spatial AI that we are looking into trajectory planning and obstacle avoidance and stuff like that. The real trick and real problem happens when we have physical contact, because when you have physical contact, then you have instability issues, then we have the energy flow issues, then we have all the issues that basically we want to see those into let's say in non-physical scenarios. I would like to conclude, and I would like to thank my team and also different European projects that contributed to these works, including two ERCs and a couple of international European projects. My apologies again for not being there, but my heart and mind is with you, and I hope you're enjoying the workshops. Thank you very much.
Hello. So thank you for your presentations. So I'm started working on this area of interest. So I have a questions because at the beginning you just shows that tracking of human kinematic body movements, like with some RGB sensors, right? I'm not talking about RGBD. We always aware of that sometimes front view may not be appropriate to understand the human kinematics, body especially. And I see that your camera was more diagonal-wise, right? Because in certain scenario that we need the sagittal view to understand the correct kinematics, because you show the fall detection, which was side view. So if you want to make the robot more intelligent, you cannot expect all the time the front view, because in a basic scenario, in the home environment, scenario can be anywhere. And especially if you want to design the robot actions, especially the humanoids, of course, robot has their own dynamics and kinematics. You need the kinematics that is much more appropriate, which is shown by the profile view or sagittal view. What is your opinion on it?
Very good observation. I think this is the whole point we went to multi-camera modular development. So if you go to this realmove.eu, which is our new let's say startup idea. So this is multi-cameras that it looks from different angles, not only different, let's say, points of view towards the person, sagittal, front, back, but also it is very important for when you have cluttered spaces. For instance, in industrial spaces, not everything is clean. So if you have multiple cameras, you can actually have a 3D full skeletal reconstruction of the person. So this was the main reason that we are moving towards multi-camera direction. So we put 4 cameras because there were no obstacles, but in some of the works that we are working, especially in the cluttered spaces, we can go up to 10, 12, 15 cameras. So what is really nice is that our system uses low-cost cameras. So adding number of cameras, because they're also RGB, they are cheap. So it doesn't really add up to the cost of the system eventually that will be exploited in industry, healthcare, or whatever. But so imagine in every room of a patient or industrial settings, you have cameras on the ceilings that you're already using them, many of them for surveillance. But by triangulation and using some techniques that we're doing, you can have multiple views. And merging those multiple views, you can have a very reliable multi-axis understanding of the skeleton, which is makes it very robust to tracking.